Bromine water oxidation. Bromine water is a reagent that selectively oxidizes the CHO group, that means the aldehyde group, to a carboxylic acid group, thus converting an aldose to an aldonic acid. So if you take an aldose and add bromine water, then you will get aldonic acid. Because the alkaline conditions of the tolerance test also promote the equilibration of aldoses and ketoses, ketoses also give positive tolerance test. Glycosides are not oxidized by bromine water because the aldehyde carbonyl group is protected as an acetal. Thus, bromine water cannot oxidize ketones and glycosides. So, if you want to distinguish between the aldoses and ketoses, so you have to use this bromine water. Aldonic acids exist in acidic solution as lactones called aldonolactones. The lactones with 5-membered rings are somewhat more stable than those with 6-membered rings. So this is the D-glucono-delta lactone. This is the beta D-glucopyranose structure, and you are adding bromine water. So this OH group will be oxidized into this C-O group. Now this is the structure of lactone, OCO. This is a lactone. Now how to give a name? If this one is your carbonyl group, this carbon is the alpha carbon, this one is the beta, this one is the gamma, and this one is the delta. Now this O group, this oxygen group, is connected with the 4th carbon, that means in the delta carbon. That's why this is a delta lactone. So I hope you can understand how to do the nomenclature. Alpha, beta, gamma, and this one is the delta. Experiments with aldopyranoses have shown that the actual course of the reaction is somewhat more complex than it has been indicated. Bromine water specifically oxidizes the beta anomer, and the initial product that forms is a delta aldonolactone. This compound may then hydrolyze to an aldonic acid, and the aldonic acid may undergo a subsequent ring closure to form a gamma aldonolactone. So what is the course of the reaction? You have this D-gluconic acid. Oh no, not this one. Actually, start with this. Oh, I'm confused actually. You have got this delta lactone here, and now if you add some water, then you will get this gluconic acid. Now after this, in case of delta, this OH was in the ring formation. This OH was involved in the ring formation, but after adding water, you have got this gluconic acid. Now this OH can also make the ring, a 5-member ring. So this will be a gamma gluconolactone. You know the nomenclature. Again, this one is alpha, this one is the beta, this one is the gamma. So this oxygen is connected with the gamma carbon. That's why this will be the gamma gluconolactone. This is the structure. Okay, this is the entire course of this oxidation. First you take this beta D glucopyranose, then add bromine water, then this OH will be converted into C-O. That means a lactone will form. As this oxygen is connected with the delta carbon, so you are getting a delta lactone. Then add some water, you will get a gluconic acid, and this gluconic acid will be in equilibrium with this gamma lactone. This OH is attacking here and forming this cyclic structure which is a D-gluconic gamma lactone. Now see the detailed mechanism of oxidation. You have bromine water. That means this bromine water means HOBr plus HBr. You know bromine can just break bromine. This, if you take this Br2, if you take this Br2, so after this heterolytic cleavage, one will become Br minus, another one become Br plus. So the Br minus will take a proton and form HBr, and the Br plus will form HOBr, where Br is plus here, this Br is plus, this Br is plus and OH is minus, and here this Br is in minus oxidation state. So after this oxygen will take up another proton and this will form this. Now this carbonyl group, this oxygen can attack this Br, this one, because this has become a good living group. So now just follow the reaction mechanism. At first water is attacking this carbon, and simultaneously this lone pair of oxygen is attacking this Br. So you are getting this structure. After the deprotonation you will get this, and now this hydrogen will leave becoming HBr. This hydrogen and this bromine will leave. So you will get this aldonic acid. Similarly, just look at the beta D-glucopyranose, the chair form. This oxygen will attack this bromine, which comes from this HOBr, and then this hydrogen will leave being HBr, and then you will get D-glucono-delta lactone. Now beta D-glucopyranose undergoes oxidation by bromine water 250 times faster than alpha D-glucopyranose. Now see what is the case. This is the beta D-glucopyranose, which can oxidize faster than this alpha D-glucopyranose. Why so? Because in case of beta D-glucopyranose, this H and this Br are anti-periplanar. That's why the E2 reaction, the elimination reaction, occurs much more easily. So you are getting D-glucono-delta lactone. But in case of alpha D-glucopyranose, when you treat it with bromine water, then if this H is here, because the hydrogen is in equatorial position, you have to keep this bromine here so that it can become anti-periplanar. But this bromine feels some repulsion with these hydrogens, the hydrogen of this 3 and 5 carbon. This is also said 1,3 diaxial strain. So because of this repulsion, this bromine cannot be in the anti-periplanar arrangement. So this bromine adopts this syn-periplanar arrangement, and which doesn't readily gives the E2 reaction. That's why this alpha D-glucopyranose is very much slower in case of the oxidation than the beta D-glucopyranose. Now just read it. In case of beta anomer, C, H and O Br bonds are anti-periplanar to each other, or the anti-parallel to each other. The stereoelectronic requirement for an E2 reaction is the anti-periplanar arrangement of the departing groups, Also, the elimination of a proton from the axial position is more favorable than from an equatorial position. In alpha anomer, the axial hydrogen atoms at C3 and C5 hinder the antiperiplanar arrangement of CH and OBr bonds, and actually it takes up a syn periplanar conformation, from which elimination of HBr does not take place. The very slow rate of the oxidation of alpha anomer is due to its conversion to the beta anomer, and then it follows the oxidation. So the alpha anomer first converts into the beta anomer and then it is oxidized.